In addition to the sample size, we also have one other thing that we can change to affect power, and that is our alpha level, or our standard of evidence. Remember, we set our alpha level. We decide which sample outcomes count as evidence enough to reject the null hypothesis. So, if we relax or make more strict our alpha level, we'll change which sample outcomes allow us to reject the null. Let's go back to the distribution under the null hypothesis. Let's look at it in the original circumstance. Now here we have the critical regions with alpha of 0.05. If we were to relax our alpha level, that is, choose a less strict criterion, for instance an alpha of 0.10, notice what this does to the critical regions. Our critical regions shift closer to 0 under the null hypothesis. That is, we are counting more samples as counting as evidence against the null hypothesis. Now going back to the diagram with both of our distributions, here it is with alpha of 0.05. If we were to shift our alpha to 0.10, what we'll do is count a little bit more of that distribution under the alternative hypothesis as counting as evidence. Let me shift back to 0.05 and pay attention to the region that's changing. Notice that there are samples under the alternative hypothesis that can count as evidence now that didn't count as evidence before. So this change will affect power, but it will also affect our false alarm rate. Notice that if we were taking our sample from the distribution under the null hypothesis, so a situation where the null is actually true, changing our alpha value is changing the proportion of the time we false alarm. Remember, alpha is exactly equal to our false alarm rate if the null hypothesis is true. So, changing alpha has consequences in both circumstances. When the null hypothesis is true, it changes our false alarm rate, but if the alternative hypothesis is true, it changes our power. Now let's try a different circumstance. What if we made our criterion even more strict? That is, we wanted to count only the least likely 1% of sample outcomes as evidence against the null hypothesis. Notice that puts our critical regions much further in the tail. We're counting fewer of the samples as evidence enough to reject the null hypothesis. Going forward to our diagram with both distributions, here we are with an alpha of 0.10. Notice what happens when we change to an alpha of 0.01. This cuts considerably into the distribution of z sub x bars if h1 is true. I'll toggle back and forth and pay attention to where the cut point is changing. Notice that with a smaller alpha, an alpha of 0.01, we're no longer counting many of those sample outcomes as evidence enough to reject the null. But in this case, we've reduced our false alarm rate if the null is true. So this is a trade-off between our false alarm rate if the null is true and our power if the alternative is true.